It's 10:30, so I'm going to begin the class. If you have any questions, please let me know. I know that the second homework is out. Oh, not yet, but probably today. And you will have about 10 days, or is it about 10 days? About a week? About 2 weeks. It's long. It's long. Okay? But, try your best. If you have any questions, please put it up on the board or, send me email. Actually, the best thing to do is to put it up in the board, KLMS board, and we'll try to answer it as soon as possible. Okay? So the second homework will be out today, and it's long, so start early. And the midterm, will cover the first homework and the second homework. Okay? Questions? Questions? Okay. If there's no question, I'm going to begin the class. Someone has mentioned that, this, because they haven't had probability, that this is maybe a little bit difficult for them. I've not used much, I have explained the material in terms of probability, but all the probabilities that you need to know is contained in this course, okay? Because all the inequalities regarding the probability and also in the proofs. The only probability that is probability of union of a set is upper bounded by the sum of the probability of each of the events, okay? That's, but that's coming from me, who've had a lot of probability. So for students who have not had probability, maybe it's not so easy. But anyways, so my plan for today is I went over this topic of non-uniform learnability and structural risk minimization, SRM, sort of quickly last time, so I'm going to go over it again. And then I'm going to start another topic, which is called ensemble learning. And in particular, I'm going to be focused on this algorithm called boosting. Okay. Non-uniform learnability. Just to recap, we learned what epsilon representative was. This is a property of the sample, okay? And it's saying that for these samples, these set of samples, the training loss and the test loss are very, very close, okay? So it's this property, epsilon representative, okay? As simple as that. Uniform convergence, if you have more than that, then with this probability, the sample is going to be epsilon representative, okay? Okay, so if you have uniform convergence with respect to this hypothesis and you have more samples than this, then this is going to be true. Your training loss and the test loss are going to be very, very close. That's what this is saying, okay? And then we also talked about agnostic pack learnability. And this is so the function that you have here, it's written as a function, okay? The hypothesis that you found from some method, using some method, the test loss of that, this was found using the training loss. F theta was found by the training loss. Some algorithm, okay? And ERM would be one algorithm. And you found your F theta. The test loss of that will be upper bounded by the minimum test loss plus epsilon. This happens if your sample is greater than the sample complexity of this hypothesis class. Okay? Then, if this is true for all different types of distribution source, then it's going to be agnostic pack learnable. Okay? If this property is satisfied, then it's agnostic pack learnable. Okay? So this has to exist. This has to exist. Okay? This has to exist for this hypothesis class. And for uniform convergence, this has to exist. Okay? This has to exist. And it turns out, so this is, agnostic pack is a bound on the test loss of the function that you found, which is upper bounded by this. Okay? And sometimes we are also interested in how far is your training loss compared to the test loss. Okay? And if we assume epsilon representative, then let's say you use your ERM. You can go through this. You can find the training loss here is upper bounded by the best possible test loss plus 2 epsilon. Okay? You can go through this. Now, this is with regards to uniform convergence property. Uniform convergence. Why is it uniform? I'm going to be talking about non-uniform. For some sample complexity, which is not a function of the hypothesis, but only for epsilon delta, if you have more samples than that, then this is true. Then that is true. Okay? Irrespective of the hypotheses. Epsilon delta. Now, non-uniform, let me just say, non-uniform, so it says uniform convergence, there exists a single sample size such that the empirical risk of all hypotheses in H is within epsilon of the risk with high probability. Well, you can also say that. So here I've said that the test loss and the best loss are only 2 epsilon away. And also, if you have uniform convergence, then your test loss, your training loss and the test loss are just epsilon away, very, very close. Okay, that's. Now, what I'm going to do is I have a hypotheses class that's really, really large. It's huge, okay? And it's not very difficult to find this sample to satisfy the uniform convergence property. So what I'm going to do is define non-uniform convergence, and it's going to be close to point-wise convergence. Point-wise convergence means that each hypothesis is going to have its own rate, meaning that it's going to have its own sample complexity. Okay? So let's say your hypothesis class has a first order polynomial, second order polynomial, and third order polynomial. You know that the first order polynomial would require a small amount of data to train than the third order polynomial. Okay, the sample complexity will be different for different hypotheses of different complexity. Okay, uniform convergence had just one sample complexity for all the hypotheses in the hypothesis class. This one, we're defining it so that the sample complexity is a function of the hypotheses. So there's this H. Then you're going to say something like this. The test loss on the hypotheses that we found by some algorithm is going to be, the test loss is going to be upper bounded by any hypotheses plus epsilon. Okay, and that happens. So this is being far away from epsilon, far away from this. What's the probability of this being far away from that? That probability is being less than that, not far away, close to that. That probability is very high if delta is small. That's what this is saying. Okay, so that's non-uniform learnability. There is this function, there is this sample complexity. So it's a function that takes epsilon, delta, and the hypotheses and gives you an integer number, or not integer number, a natural number, 53 or 65, and say if you have more than 65 samples or 53 samples, then this is going to be true. That is non-uniform learnability. So our hypotheses, consider a task where you have a real number and you're trying to classify it as -1 or 1, okay? And you have different degrees of polynomial. Hn will be the polynomial of degree. And I'm considering all the polynomials, first order, second order, and my classifier looks like this. Okay, Px is a polynomial, and I'm looking at the sign of that, and that would, give me -1 or 1, right? And this polynomial could be everything. And we know that the VC dimension, I mentioned this thing last time, the VC dimension of an nth order polynomial is n plus 1. Okay, that can be proven very, very easily. Okay, so the hypotheses of all the polynomials will be the union of the nth order polynomials. So n will be polynomial of first order, polynomial of second order, polynomial of third order, right? So the hypothesis class of the polynomial would be the union of first order, second order, third order, and so forth. Okay? Now, each of these polynomials of nth degree, because it has a finite VC dimension, it's pack learnable or agnostic pack learnable, right? We learned that. But what is the VC dimension of H here? Each one has a finite VC. What is the union, infinite union of the hypothesis nth order polynomial? It's going to be infinite, right? So we also learned that when a hypothesis class has infinite VC dimension, then it's not pack learnable. Okay? And what I mean by pack learnable is that statement again, the test loss being upper bounded by the best one plus epsilon, or the training loss being upper bounded by the test loss and epsilon. Okay? So this is, infinite VC dimension, but this one is finite VC dimension. So is this no good? Oh, it's but there's this algorithm called structural risk minimization. Okay. And what this is doing, let me just show you. Structural risk minimization provides a principle or theoretical approach to controlling, overfitting, or explicitly trading off empirical risk against hypothesis complexity. So this is a little bit different from what infinite VC dimension, but it's working with hypothesis class that may be infinite VC dimension, but it's comparing. It has some groups of hypotheses. It's a union of various hypotheses of different VC dimension, and it's comparing its generalization ability. So let me just say it in another way. I have a first order polynomial, second order polynomial, and third order polynomial, and so on. Okay? Which is infinite VC dimension. And I have some data and some task, and what SRM is going to do is going to compare the different hypotheses groups. It's going to look at the empirical risk of each of the different hypotheses group. And because just comparing the empirical risk is unfair, because the second order polynomial is going to be always better than the first order polynomial. The third order polynomial is always going to be the second order polynomial. So it's going to add on some complexity measure. Okay, so the first order polynomial, because it's simple and it's weak, it has less it's going to have less complexity, so it's going to be somehow, the confidence interval is going to be less. And if you have higher order polynomials, you're going to add on more, you're going to penalize it. So it's like comparing a first grade student with a second grade student, and you want to see how well it's going to do on the test data. You know that the second grade student is always going to be better than the first grade student, but maybe first grade student is good enough. Huh? So the second year grade, you're going to give the same problem to the first first grade student and the second grade student, but you're going to penalize the second grade student a little bit. Maybe when he's solving the problem, he has to close his eyes, one of the eyes, to make it a fair comparison between the hypotheses. Okay. And this relates to, regularization, early stopping in neural networks, and complexity-based model selection. Okay, and then I'll just explain this thing just a little bit more. So I have a hypothesis class which may have VC dimension that is infinite, but what I'm going to do is I'm going to structure it so that it's a union of small groups, hypothesis groups, okay, or hypothesis, and each one and the hypotheses will be nested. So an example that I've been using all the time for this lecture is first order polynomial, second order polynomial. Second order polynomial can represent a first order polynomial completely. Third order polynomial can represent a second order polynomial. So the polynomials or the hypotheses in this case is nested. And polynomial classes is just one example. Okay? And each of these groups will have a VC dimension, finite VC dimension, certain, finite. So it's pack learnable. And the VC dimension will be of increasing order. So this one may be 3, this one will be 4, 5, 10, 15, and so forth. So the hypothesis class would have more complexity, would have better ability to represent the data. Okay? So it's not only VC dimension, you can generalize this to maybe increasing Rademacher complexities. Okay. And so this hypothesis is vast. It's huge hypothesis class, and I want to, pick out a hypothesis that would give me good low test error. Okay? So if it's infinite VC dimension, if you find out that it's going to be infinite, then, by our VC theory, it will be, it will not be learnable. Okay? I would not be able to bound the test error on the hypothesis that I find. Okay? But by structuring it this way, what I can do, structure it this way, I find the ERM for each one of them. ERM is a hypothesis. So this group would have it's a first order polynomial. So there's an infinite number of hypotheses, right? I pick out the best one that would minimize the training error. So I'm given the training data and I apply it here and I pick out one. I could pick out one from H2. I could pick out one from each one of the hypotheses class. Okay? So now it's like, oh, I pick out the best one from here, I pick out the best one from here, I pick out the best one from here and here. How do you compare them? Compare them, and you need to select one that would give you the best test error. So we learned about this. One example of this nested is this polynomial. Okay, this polynomial of degree n would have a VC dimension of n plus 1. So we could first order, second order, and third order, and fourth order will be a nested. And SRM looks at this. It looks at the test error, another training error, plus you add a complexity penalty for each of the hypotheses. Okay? And this penalty, there are different ways to put these penalties. These penalties are generally a function of the VC dimension, or it could be a function of the router marker. Okay? So, for each one, I found the training error. Okay? Obviously, in general, the training error for the hypothesis that you found in H2 will be smaller than the training error that you found for H1. All right? As you go with higher VC dimension, the training error is going to go down. Right? But what you're going to do is put complexity penalty on each of the hypotheses. So let's say this has training error 5, this one 2, this one 1. But let's say this is, okay, so let's give it a number. This one is 5. The other one is 3, let's say that's 2. And the complexity penalty is 3. This one might be 4. And this one has 0. Then you would choose, so this is the penalty. This is the training loss. And you add these two to figure out the best one. That's the idea for structural risk minimization. And I just like to just say that structural risk minimization, the first paper on structural risk minimization came from Vatnik. So he used VC dimension to quantify the complexity penalty. But, you can put in, different, there are various ways to define the complexity penalty. Okay? So I just want to just say that, okay, so let the VC dimension is this. VC theory gave you this. I found a hypothesis that minimizes the training error. Okay, I found H. it's going to have a test error that's bounded above by its training plus this. Okay? D represents the VC dimension here. M is the number of training data. And delta. Now, in the structural risk minimization, there are a number of ways to do this. The delta the deltas are weighted depending on the hypotheses. So, what do I mean by this? So this is what I do. Let's say I have a delta that I need to get, okay? There's a delta that I need to get. I weight it by this Wn. Now the Wn that is often used is this. This one puts the same delta. So if I had n hypotheses, then the weights are equally weighted. This one puts the largest weight on the lowest hypotheses. What I mean by lowest, put the lowest weight on the nested hypotheses. Where is it? Lowest delta and higher. Okay, so 1/2, the next one is 1/4, and so forth. So I'm putting higher probability, make it more, so if the delta goes down, so this is the weight that I'm going to use, delta times Wn. So for H1, it will be delta times 1/2. For H2, it will be 1/4 of a delta, and so forth. But if you add up from n equal, I think, 1 to infinity, it adds up to 1. So this one would have, in order to satisfy greater or less than epsilon, which is 1 minus delta, 1 minus 1/2 of delta, this one would have a higher probability. This one will have a sort of a lower probability than H1. So I'm putting different deltas for different hypotheses. And when I add up all the deltas, it adds to 1. Okay? And I'm using all the data for each of the hypotheses class. So in the beginning, I said that different hypotheses class would probably require different sample complexity. But that problem is very, very difficult to determine, the sample complexity for different hypothesis class. So instead, we use all the training data for all the hypotheses class, for all the hypotheses, but we use a different delta. And different deltas will lead to different epsilon, and it will lead to different complex complexity. Okay? Okay, so that's structural risk minimization. So let me just summarize. I'm given a hypothesis class that's very, very large and complex. So I structure it into something that is nested. Okay? And I have it so that it's in ascending VC dimension. I find the ERM for each of them using the same number of training data. Okay? But for each hypothesis, I'm going to add on a different complexity penalty. And when I add that on, I'm going to make the comparison. I'm going to pick the hypothesis class or the hypothesis in in one of these nested hypotheses that minimizes this quantity here. This plus that. I'm going to pick the hypothesis. So the hypothesis will be coming from each of the hypotheses will be coming from different nested hypotheses class. Okay? But there's a complexity term, and the way you would use this complexity term, it also involves VC dimension and also different delta. Okay? And the deltas will be weighted. Okay, and some of the weights that's used is here. So if you have a large, so in the lower hypothesis class would have a larger weight. So it would have a lower confidence. 1 minus, remember the delta, will have lower confidence. So the probability of that being picked up will be greater. And that would lead to a different epsilon. It would lead to a different epsilon value. Okay? So rather going into more details, I stop here because I just want you to understand this conceptually. Okay. Same training, okay? So I think I've said enough. And I want to move on to a different topic. Any questions? Any questions about structural risk minimization? Okay. It stems from non-uniform learnability. Okay. So you want to use, what we want is to compare hypotheses with different VC dimension using different number of training data. That's difficult. So what we do is we penalize it differently, complexity, in terms of complexity. We penalize it differently. And this idea is related to regularization that we use for doing a lot of different things in machine learning. Okay, so if there's no questions, I'm going to talk about ensemble learning. So ensemble learning is having many classifiers or models to solve a task. So rather than having one model to solve the task, you have many. Okay? So, one may be weak maybe it's good to have many. Now, obviously, if you had many models of the same size, then computationally wise, it will be difficult. Okay, I have one strong model. Obviously, if I have 2 or 3 or 4 strong models, it's going to, perform better. That's a no-brainer. But you have to have more resource, okay, in terms of memory and electricity and various things to learn. So what we will be talking about is to have not one strong model, but maybe a number of weak models to produce result that is better than one model, and the computation will be similar. Okay? So the fixed parameter will be equal complexity, but this one is one big model, and this ensemble will be weaker models, many weaker models put together. Okay? But ensemble learning, it's a general approach in machine learning that seeks better predictive performance by combining prediction from multiple distinct models. So, in the definition of ensemble learning, there is nothing that says about the computational ability or the memory. There's no restriction on that. There are 3 ensemble methods that we can think of. Okay? And I'll be focusing on the third one. Let me explain. Bagging ensemble. I have a training data. I have a large training data. And what I'm going to do is I'm going to sample. I'm going to close my eyes and sample from this training data. And I can create many different samples. And from that, this slide shows trees, which is a classifier, a very simple classifier. Okay. I could create many classifiers. It doesn't have to be trees. It could be, many other things. Okay. So all these classifiers or models, predictors, will be slightly different because it's trained on different data, and they are somehow combined to produce some output. Generally, these models are low biased. So they have high capacity. High capacity. So in my previous slide, I said weak stick, but these sticks are generally fairly big sticks. Okay? So if there are big sticks, what is the problem? You know that it's going to be low bias. What about the variance? Generally, model of bigger size have low bias, and it also has high variance. Okay. So by combining high bias and low bias and high variance, you can reduce the variance. So this combined thing will have low variance and high bias. Okay? That's bagging. That's one method. Stacking. So all of these trees or models are homogeneous. Their complexity is the same. They come from the same algorithm. Okay? But they're just trained on different data. Here, you have the same data, but different models. So these are different models. It may be completely different. This may be SVM. This may be some deep learning architecture. This may be KNN. Different models, but trained on the same data. And you have a model called the meta model, which combines the output of all of these to produce the best result. Okay? That's stacking. The third type is constructed in a sort of a sequential manner, and it will be sort of a sequential manner. So you have training data, you find the model, the first model, and then you find out what the model is deficient in, and you train it on the second model. Then you find something that is deficient with first and second model, and then you reinforce it with model 3. And you do this, you keep on doing it. And then you somehow combine this in a weighted manner to produce the best possible output. Okay? And I'll be focusing on this model, this ensemble method, called eta boosting, okay? Which was thought to be, which was thought to never overfit. Meaning that I can go on forever, and the model will be very complicated, or the complexity would grow. That model on test data would do very well, and if I keep on going to infinity, The training error is going to go low, and also the test data. That's what people thought for the longest time. But it's been found that this one also overfits. So, by the way, this algorithm, ADA boosting, was developed by these two guys, Robert Shapiri and Jörg Freud. They used to work for AT&T, a telephone company that classified incoming calls. Incoming calls is either regular calls, it may be a collect call, various types of calls, okay? And they had an operator who would listen to the caller and classify them. And the operators would receive a lot of money. So the telephone company wanted to replace all of them by a machine learning algorithm. So these two came up with this algorithm called ADA boosting, and it won the Gödel Prize. Okay, so it's an award-winning algorithm. Okay, 2003, and let me just give you a brief. The little sticks. I showed you in the in the second slide, a big model, one big model, and small models, small sticks, thin sticks, weaker sticks. And the weaker sticks, I'm going to combine these weaker sticks, the weaker, oops. The weaker sticks are called weak classifier. Oops. So it's weak. I combine them, the sum of weak classifiers. And the weak classifier has this property. The test loss on this weak classifier will be slightly better than tossing a coin. So if we're doing binary classification, and you're making a decision based on that, then what is the test error on that? What would be the test error on tossing a coin to make the decision? It will be half. Half of the time you will be correct, half of the time you will be incorrect. This weak classifier would have a test loss that is slightly better than tossing a coin. Gamma is a positive number here. 이거 어떻게 없어? 안 꺼지게 할 수 있나? Okay. Anyways, so let me just give you a quick rundown on this algorithm, and then I'm going to show you a sort of a toy example of how. So I'm going to be focusing on this algorithm called ADA boosting. And so the problem is I have data and label. I'm considering binary classification. So the label is either -1 or +1. Okay? And I'm going to have a weak classifier. And the weak classifiers, there's a whole class of weak classifiers. And at each iteration, I'm going to choose one weak classifier. And I'm going to call it GK. So K represents iterations. So if you go back here, so here is the first iteration, K equals 1. Second iteration, K equals 2, and so forth. So it's an iterative, and I'm adding on these weak classifiers. And those will be called GK. And my final classifier would combine these weak classifiers, but I'm going to do a weighted sum. Weighted sum. So each weak classifiers are going to be weighted by some alpha t. I'm going to take the sum of it, and what I'm going to do is I'm going to place a sign on it. Sign will give me either +1 or -1. Okay? So that will be my final classifier after going through T iteration, big T iteration. Now, ADA boosting has weights on the data. That's the thing. You have to remember, there are training data, and each of the training example will have a weight. And that weight is going to be updated at each iteration. So, in the beginning, each of the data will be equally weighted. So there are n training examples in the training set, and each one will have equal weights. Okay, let me explain how the iteration is going to go, and I'm going to show you an example. So I'm going to go through T iteration, big T iteration, and I'm going to choose a weak classifier that minimizes the weighted error. It's weighted error because each of the training data has a weight now, okay? And that weight is going to change at each iteration. And actually what's going to happen on data, it doesn't do well or it fails, the weight will go up. And for data that it does well, the weight is going to go down. Okay? So I'm going to choose one particular weak classifier, and I'm going to call that GKT, that minimizes this error. So my prediction, my ground truth, I'm going to see whether it's right or wrong. If it's wrong, I get a value 1. but there's going to be a weight on that ith data. Okay, I want to pick one weak classifier. Okay, I'm also going to calculate or evaluate the weight that I'm going to place on that particular weak classifier. So at each iteration, I'm going to choose one weak classifier and I'm going to put a weight on that. And that weight is alpha t. And if you look, it's, well, I'm going to go tell you why it's this, but this epsilon t is the error, and it's going to be less than half. Okay, it's going to be less than half. Okay, it's because it's a little bit better than tossing a coin. So if you look, this one is a little bit less than a half. This one is a little bit above a half. So this value is going to be above a 1. Natural log above a 1 is going to be a positive value. So this is a positive value. So you're going to put a positive weight on the classifier. And the weight on each of the data is going to change. And this is how it's going to change. This is the weight of the data before and after the classifier, it's going to be updated. So this is the ith data, and it's going to be updated from t to t plus 1. And let's have a look. This is the prediction on the ith data. This is the ground truth of the ith data. If the signs, if the prediction and the ground truth are the same, this will be a positive value. And I have a negative here. So, and there's this normalizing ZT. Okay, so all the training data, when you add up the weight of all the training data, they add up to 1. ZT is there so that when you add up the weight of all at iteration t plus 1, they add up to 1. You see that? So this is positive value. If my prediction and the ground truth are the same, there's no error, then this exponential to the negative value, so this will be a smaller value than 1, and the weight will decrease. If they don't agree, this will be a positive value, and the weight will grow. Okay? So for the ith data, if it's misclassified, the weight goes up. If it's correctly classified, the weight goes down. Okay? And if the error is small, then the weight on the classifier is bigger. So let me give you an example. Let's do this thing and then I'll just... Here is pluses and minuses. Obviously, I want to classify, plus and minus correctly. And my weak classifier are classifying, it's aligned with the axis of the feature. So my first one that does the best job is this G1. Okay? And I'm going to put circles to denote the weight, to denote incorrectly classified, and I'm going to change the size of the data. Okay, that represents the weight. So G1 does the classification. It got, out of the 10 things, it got 3 things wrong. 3 things wrong. And the alpha 1 was this. And we do a weight update, and you see these 3, the weight has grown because it was misclassified, while the others, the weight has been reduced. I find G2, okay, that minimizes the weighted error. And for these, the circles represent misclassified, so the weight goes up. And these they were misclassified, but now correctly classified, so the size has been reduced. And I keep on doing it. G3. And it turns out my final classifier is G1, G2, G3. And the green represents the alpha T's. Okay? And that will be my final classifier. So weighted sum of the classifier, weak classifiers. Okay? This algorithm is very simple to run, very, very effective. It works really, really well on training data. Okay? And we're going to analyze this next time. Okay?